All right, well, welcome back. I'll have to make these announcements again at the end of class, clearly. But a couple of quick announcements about administrative stuff. The last homework is out. It's due next Tuesday. We are, at least at the moment, still planning to actually grade this. And in particular, that means we need to be able to have them available to give back to you. We're going to aim for Friday. Okay, so it'll come in on Tuesday, and then by Friday, which I realize is still in the middle of exam week, we'll have your graded solutions back. We're going to continue running office hours until the actual final exam, and we're very likely to be running a review session the weekend before the final, either Saturday or Sunday. And so you can come to office hours, or you can come to the review session to actually pick up your graded homework if you want feedback. Let's see. On Thursday, at the end of class, I'm going to distribute ISIS forms. So if you have friends that regularly stay home and watch the lectures in their dorms in their pajamas, or just don't feel like coming across campus when it's cold, please strongly encourage them to come for at least the last 15 minutes of class on Thursday. Because if you're not physically here, I can't give you the forms. The ISIS forms, as you know, are the official feedback mechanism for how we're teaching. This is where you get to give me a grade which goes on my permanent record. And more importantly, for me, you get to give me narrative feedback describing what you think was successful or wasn't successful about the way we ran this course. Filling out these forms is always important, but in particular for this class, because it is a pilot offering for a class that's going to be required and taught forever, we really need your feedback. We really do need people to come and write comments on these forms. There's a fair chance that we'll release a more detailed survey and ask people to fill it out after the class is completely done. But while the class is still fresh in your minds, if you can tell us what worked, if you can tell us what didn't, if you could tell us what was just complete failure versus what worked really well, this is information that we can carry forward to future offerings in the class, not only when I'm teaching it, but when other people are teaching it. Let's see, what else? Conflict exam. So the regular exam is 2 weeks from today in the evening. The conflict exam is 2 weeks from today in the morning. So let's see, today's the 2nd, so the regular exam is the same thing, only it's in the evening. I'm going to post a registration form later today. Anyone who wants to take the conflict exam can, but I just need to know how many people that is. Okay, so if you prefer to not wake up at 7:30 in the morning and trudge through the cold, but rather prefer to first take the exam and then trudge home through the cold and the dark. Great, take the regular exam. If you would rather do it in the morning and get it done with, great, take the morning exam. I just need to know how many people are in each so I can schedule an appropriate room. As I said, there'll be a review session either Saturday or Sunday before the final. The last piece that needs to go in here, next Tuesday is the official last lecture for the class. Traditionally, I use the last class meeting to answer questions, maybe spend a few minutes at the beginning just going over sort of a global overview of the class, remind you what we've actually done. But mostly, I will be here to answer questions. These could be questions about the final exam, but given that there's a review session coming up, only a few days before the exam, I would encourage people to bring questions that don't have something to do with the final exam. Whatever the questions are. Some questions I've gotten are things like, how did you get into this stuff? Where did you get your dog? What are you doing next semester? How do I avoid this for the rest of my life? Why did anything that you want to ask about the department, about the course material, about research, about grad school, about doing administrative academia stuff. I'm not going to be able to say that much about, basketball or anime. But I'll just say I don't know, take the 25% and ask for the next question. Okay, so please, any questions you like on Tuesday. Okay. So hopefully I'll remember to put this up again at the end of class. All right, so I'm going to give you a short puzzle to start off the discussion for the last topic of the semester. Here is a 5-line program, right? Written in pseudocode, but you could translate this into a 5-line Python program, or a 5-line Java program, or a 500-line C++ program. It's fairly simple. You have you get an integer and a positive integer, in fact. I'll just insist. And I'll just repeatedly loop until that integer is 1. And in each iteration of the loop, if the number is even, I'll divide it by 2. And if the number is odd, I'll multiply it by 3 and add 1. So, for example, if I start with 17, if I triple that and add 1, that's 52. That's even. That's even. That's odd, so I triple it and add 1. That's even. That's even. That's even. I'll triple that. That's odd and add 1. So, and then at this point, you can see where it's going. Okay, so the answer for 17 is, yes, eventually this program halts. And so the question is there an integer n greater than 0 that will make this program run forever? Now, you'll notice, actually, if you plug in -1, it will make the program run forever. Okay, so that's not interesting. I want positive numbers. Okay. Actually, if I change that greater than to not equal to 1, it would run forever. As it stands, a negative number would just fall out. Okay, great. So is there something that would make this run forever? The answer is we don't know. Nobody knows whether this program always runs forever. We do know because we've actually run the algorithm that if there is an integer n that makes this program run forever, that number has at least several hundred digits. Right, so we've run the program for, I think it's all n less than 10 to the 120th. And for each one of those, yeah, it terminated. But that's only a finite number of examples, and there are an infinite number of things we could plug in here, yeah, maybe you could think of it as strong evidence, but we don't have a proof. And so, seeing this problem for the first time, you might reasonably ask the question, isn't there a computer program? Isn't there an automatic way I could just plug this 5 lines of code into something like a compiler, and it would tell me whether it's possible for this thing to get stuck in an infinite loop? But there's no such program. We know that. We know that there is no program that can take in an arbitrary piece of code and report correctly, this code can never get stuck in an infinite loop, or yes, this code can get stuck into an infinite loop. Right? Now, that doesn't mean that this problem, this particular question, will never be answered. It just means that there's no sort of automatic way to answer this kind of question for all programs using a single common piece of code. A single loop detector can't be written. Maybe there's a loop detector for this particular algorithm, but in general, we can't actually. There's no systematic solution that would apply to arbitrary pieces of code. Okay, so here's a different puzzle. So I have 3 stacks of cards, and on all the cards in each stack are identical. And for each card, there's 2 strings written on it, one in green and one in red. So what I would like to do is choose a sequence of cards, each card coming from a different stack, so that when I line up the cards, I get the same string in green as I get in red, just broken up in different places. Okay? So here are 3 stacks of cards. So in this particular case, there's a solution that uses 4 cards, right? So specifically, I use the 4th card, and then I use the card from the 3rd deck, and then I use a card from the 2nd deck, then I use another card from the 3rd deck, and then I use a card from the 1st deck. And if I write down the corresponding strings in red, you'll see why this is a solution. Okay, so both red and green give you the string 1, 1, 0, 0, 1, 1, 1, 0, 0. Just green breaks it up in a slightly different way than red. Okay? All right, so here the answer is yes, there is a solution to this puzzle. Given a deck, and I can use, in principle, I could use each of these cards as many times as I want. So if I take these 4 cards and just repeat them again, I get a solution that uses 8 cards. Okay? So once I have one solution, I have an infinite number. Okay, so here's another example of the same puzzle. I've got now 4 decks of cards. And the question is, can I play this game where I deal out cards from each of these 4 decks in some order and eventually get to a point where the green string on the top of the cards and the red string on the bottom of the cards is identical? So in this case, the answer turns out to be yes. But the shortest solution uses 451 cards. Okay. In general, you might ask, maybe I can write a piece of code that could solve this problem. Right? The input is just a finite sequence of a finite set of strings or pairs of strings. Deck 1, there's a red string and a green string. Deck 2, there's a red string and a green string. Up to deck n, there's a red string and a green string. So you get 2 n strings. And I'm answering a simple yes-no question about them. Can I pick out a sequence of integers, pull a card from deck 3, then pull a card from deck 1, then pull a card from deck 17, and so on? That guarantees that the green string at the top of the cards and the red string at the bottom of the cards are the same, just broken up in different ways. There is no such algorithm. This problem is actually called the something was first proposed by a logician named Emil Post. This is the post correspondence problem. And it has provably no solution. There is no algorithm that can answer this question. Okay? And so there's a couple of specific instances, some of which kind of more look like pattern matching puzzles, some of which look like questions you could ask about computer programs. Is there a computer program that can automatically detect infinite loops in some other piece of code? Right? Where we can prove that there's no solution, there's no algorithm. It's not just that the problem is hard to do efficiently, it's not an example of something that you would call NP-hard, because there is an algorithm, but it's slow. It just can't be done at all. Okay, and so a reasonable question is just, well, how do you prove something like that? How do you even wrap your head around the idea formally that there are questions that just don't have answers? Okay. So to formalize this, I need to nail down exactly what I mean by there's no algorithm to solve this problem. Okay. And the way that I'm going to do this is using Turing machines, again, just the way that we did with NP-hardness. Okay. So if you remember, a given Turing machine can do 3 different things when it's given a string as input. It can run for a while, but eventually reach an accept state and halt. It's called accepting the string. It can run for a while and eventually reach the reject state and halt. That's called the rejecting the string. Or it can just run forever. This is diverging on the string. Okay, so for any Turing machine and any string, I get these 3 possible outcomes. And what this means is that I could think about languages associated with Turing machines. So, for example, I could define the accepting language of a Turing machine to be the set of all strings such that T accepts W. Right? So there is some set of strings that this Turing machine accepts. I'll call that the accepting language of the Turing machine. Right? And similarly, there's a rejecting language. There's a halting language, which is just the union of the accepting and rejecting. And there's the diverging language, which is just the complement of halt. Right? So all this means is rejects, halts on, and diverges on. Everything else is the same. Okay, so the halting language of a Turing machine is all possible input strings that make that Turing machine eventually halt, either accepting or rejecting. The diverging language of the Turing machine is everything else. Okay. So now we say that M accepts. Sorry, I guess I've been calling the Turing machines T. I'll stick to that. T accepts some language L, if and only if L is the accepting language of the machine. Okay, this is just a synonym. This is exactly like what we say with DFAs. We say that a DFA accepts a language if that language contains every string that leads to an accepting state and no string that does not lead to an accepting state. Okay. But there's a slight ambiguity here, which is I don't specify exactly what happens to the strings that are not in L. I know that if T accepts the language L, any string that's not in L won't be accepted, but there are two ways you cannot be accepted. You cannot be accepted because you're actually rejected, and you could not be rejected because the machine just never makes up its mind. Right? So there's a stronger statement that you can make, that a Turing machine decides a language if it definitively gives the answer yes or no to every string, and it accepts the language. So if L is the accepting language of the machine, and the diverging language of the machine is empty. Or equivalently, the halting language of the machine is sigma star. Or equivalently, the rejecting language of T is the complement of L. Okay? So when I talk about a problem being decidable, what I mean is a problem I think of as a language, and I'm trying to figure out, yes, I'm in the language, or no, I'm not. When I say that a problem is decidable, I mean there is a Turing machine that decides it. There's a Turing machine that definitively gives you a yes or no answer for every possible input. And the yeses correspond to strings in the language, and the no's correspond to strings that are not in the language. Okay? So this is L is decidable if some Turing machine decides it. And similarly, L is acceptable. This is a weaker notion if some Turing machine accepts it. So when I talk about a language being undecidable, it means there is no Turing machine that can definitively tell you yes or no for every string. If I tell you that a language is unacceptable, that's an even stronger statement. So all acceptable requires is that if the string is in the language, eventually the Turing machine will tell you yes. And if it's not in the language, it won't tell you yes, but it may or may not actually tell you no. Okay? We'll see some examples of this eventually. I'm not going to focus a whole lot on whether or not languages are acceptable because it's kind of broken. Another way to describe a Turing machine that describes a language, that decides a language, is an algorithm for that language. If the Turing machine can wander off and never halt on some input, it's not really an algorithm. It's not something that, for the middle half of the class we would consider to be reasonable as a solution. It's sort of one-sided, and we don't really know if it hasn't returned yet whether it's ever going to. There are some things that make it run off into infinity. It's like, no, this doesn't solve the problem. Solving the problem means you get a yes answer or a no answer. Right? I just want to make this distinction so that you don't think that getting the yes answers right is enough. You also have to get the no answers right. Okay? All right, so when I talk about there's no algorithm for a problem, it means that the language associated with the problem is undecidable. Right? The post-correspondence problem, the input is a string of zeros and ones and maybe boxes and some, you could write this down as a string. maybe using commas or something to denote the pairs instead of putting them in boxes. So the input is a string, and the output is yes, there's a solution, or no, there isn't. So this is a decision problem. The language of all these instances where the answer is yes is a language, right? And when I say there's no solution, I mean this language is not decidable, right? Similarly, when I talk about is there a program that can sniff out infinite loops? Here, the input is, the input alphabet is whatever string of symbols your programming language uses. And the language in question is all programs in your whatever syntax you're using that never infinite loop. And when I say that there's no way to detect infinite loops, what I mean is that language is undecidable. Okay, so it's not terribly hard to prove that there are undecidable languages by using a counting argument that basically says there's a countable number of Turing machines and there's an uncountable number of languages. Therefore, done. But that's a little bit unsatisfying because it doesn't actually give you an example. So I would like to give you a concrete example of a language that is undecidable with a complete proof that it's undecidable. And you've seen, I hope, versions of this argument in the past. Okay, I'll mention a couple of I'll mention a couple of these versions. Okay, so this is the language that I want to talk about. Self-reject. Now, here I've written, M in two different roles here. So M is a Turing machine, and bracket M is some encoding of that Turing machine as a string. Now, essentially what you want to think of M without the brackets around it is a piece of executable code, and M with the brackets around it as the source code for that program. Okay. Really, when I say it's the source code of the program, what I mean is this is what you would feed to a universal Turing machine that would allow that universal Turing machine to simulate M. Right? So there's a long description of exactly how one might encode a Turing machine and how one might simulate it using universal Turing machine in the notes. The details are not particularly, of the encoding are not particularly important. You could imagine just the text that you would write down to explicitly describe the Turing machine. The states are A, B, C, D, E, F, G, H, start, reject, accept. The tape alphabet is 0, 1, 2, 3, blank, X, cross, box, something. The transition function is big table, you write out for every state symbol pair what it should do. You just write that down as though you were sending it to me by email. That is a string. And provided you just decide on some syntax in advance that the universal Turing machine can accept, I can then write a piece of code that reads what you sent me and interprets it, runs that Turing machine that you've described to me on some string that you've also sent to me. Right? That's all your universal Turing machine is, and that's all this encoding is. Just write it down as a piece of text. Okay, so I want to define this language as the set of all strings that describe Turing machines that if you feed that Turing machine its own description, it rejects. Now, this sounds a bit strange because it sort of, on the one hand, makes, at least when I first saw this, it makes me think, how does M even know what its own description is? And the answer is it doesn't have to, right? It's just there's some Turing machine, and you write it as a string, and then you feed that string to the Turing machine, and something happens. Right? The Turing machine itself internally doesn't need to know that it's trying to do something like this. It's just, there's a Turing machine that rejects every string. Because it just, from the start state, the first transition is reject. That Turing machine is in this language. It rejects everything, and therefore, in particular, it rejects its own encoding. There's a Turing machine that accepts every string that is not the encoding of a Turing machine. That is in this language. Right? There's a Turing machine that accepts all finite strings, accepts sigma star. That Turing machine would not be in this language. Okay? All right. So, claim self-reject is undecidable. Okay. So the way that I'm going to prove this is very much in the same spirit as the way that I prove something is NP-hard. I assume that there is, in fact, an algorithm, and I derive a contradiction. Except now it's not going to be this fuzzy not contradiction where, well, at this point I would have $1 million and I check my wallet. It's really an honest-to-God logical contradiction. Okay, so suppose there is a Turing machine, which I will call SR, that decides this language self-reject. Good? Okay. What happens if we feed the encoding of SR to this Turing machine? There are only 3 possibilities for what can happen. One is SR could accept this encoding. One is SR could reject this encoding. And last is SR could diverge on this encoding. Okay, so let's look at these one at a time. Suppose SR accepts its own encoding. That means that this encoding, SR, belongs to the language self-reject. Because this Turing machine, by definition, decides that language. So anything it accepts belongs to that language. But if that Turing machine is in the set self-respect, then by the definition of that language, it rejects itself. Okay, so if SR accepts its own encoding, then, by definition, SR rejects its own encoding. Okay, well, let's try the other direction then. Suppose SR rejects its own encoding. So this is SR rejected a string. Since SR decides some language L, if it rejects the string, that means that string is not in L. Okay? So if SR rejects its own encoding, then the string is not in the language that SR decides. Wait a minute. So if it rejects, then by definition, it's not one of the Turing machines that rejects its own encoding. So either it accepts or it diverges, but it can't accept, it can't reject. Right? So if SR accepts its own encoding, then by definition it rejects it. If it rejects it, then by definition it doesn't reject it. Okay, so the only thing we possibly have left is that SR diverges on its own encoding. But that's impossible, because this Turing machine makes a decision about every string. So all three of these lead you to contradictions. It can't diverge because it's deciding a language. It can't accept because if it did, then by definition it would reject. And it can't reject because if it did, then by definition it would accept. Yes?
Your claim
SR is a Turing machine. Self-reject is a language. When I say a Turing machine decides a language, it means for every string I get an answer, yes or no. That's what the verb decides means.
So is the encoding of SR an element of...
That's what we're trying to prove, actually. Right? Well, no, excuse me. I don't know. And part of the reason I don't know is the conclusion of this proof is that Turing machine SR does not exist. Okay? So follow through the logic. Suppose the encoding is an element of self-reject. Then on the one hand, by the definition of self-reject, that means SR rejects its own encoding. On the other hand, by the definition of decides, SR accepts its own encoding. So I have a contradiction. Okay? So I want to give another version of this same proof, which may be more familiar, and then come back to this again to see if the analogy helps. Yes?
So you said that...
Yes?
Earlier in the definition of decides, you said that...
Here's the definition of decides.
Yeah, so...
It accepts the language L, and it doesn't diverge on anything, which means anything that's not in L, the only thing it could do is reject it.
Oh,
okay? All right. So I want to give another example of exactly the same proof. I mean, this is Turing's proof, but I want to back up a little and give a proof of a similar argument that predates Turing's proof by about 30 years. Okay, this is Russell's barber paradox. Okay, so in a certain small town on a certain day, everybody gets a haircut. Right? It's tradition, it's law. There are no bald people, there are no babies. Everybody gets a haircut. Okay, so but there are two ways that you can get a haircut. Okay, so everyone either cuts their own hair or has their hair cut by somebody else. Okay? And by someone else, I mean someone else in the town. Everybody else in the town also got their hair cut. Right? So everyone, just think of it as everyone. Okay? Now, I'm going to define a barber to be someone who cuts the hair of everyone who did not cut their own hair. Okay? So the barber opens his doors and says, on haircut day, if you didn't cut your own hair, come see me next time. And on haircut day, if you did cut your own hair, forget it. Right? And we just assume that, it's always, everybody always does the same thing. Okay? So a barber is someone that cuts your hair if and only if you don't. Okay? And this is enforced by the barber licensing office in the town hall of the thing. In order to get a license to be a barber, you have to demonstrate that everyone in town either cuts their own hair or you cut it. Okay? There is no barber. Okay? This is the conclusion from this set of rules. No one can get a barber's license. Does anybody want to give me the proof? Who cuts the barber's hair? If the barber cuts his own hair, then the barber doesn't cut his own hair. If the barber doesn't cut his own hair, then this set of people that the barbers that are all the people whose hair the barber cuts includes the barber. So the barber cuts his hair, his own hair, if and only if he doesn't. It's impossible. Okay. All right. So if B cuts B's hair, then by definition, B doesn't cut B's hair, which implies by definition that B does cut B's hair. Right? So we get this contradiction that the definition can't actually be satisfied by anybody in the town. It's a perfectly reasonable looking definition, right? Someone from out of town could satisfy it by never cutting their hair, right? But if you live in the town and you have to cut your hair, and you either have to do it yourself or you have to ask someone else to do it, and you can only be a barber if you cut everyone's hair that didn't cut their own hair, you can't be a barber. Yes?
So you're saying that only in this town barbers are on?
No, you can cut your own hair. That's fine. It just means then you can't go to the barber.
Can your friend cut your hair?
Sure.
But it doesn't necessarily have to be barber.
No, that's right. Anybody can cut anyone else. Anybody can cut anybody's hair, right? But there's a prize. There's a 20-foot tall trophy filled with chocolate that has the word barber on it, and now you will get this prize if you satisfy that condition. Now, if your friend cuts your hair and my friend cuts my hair, then we know there's no barber because we got our hair cut by different people. Nobody wins the prize. Fine. No contradiction at all. It's completely consistent with the rules. But you might imagine the townspeople getting together and deciding, hey, let's figure out a way, let's organize our haircuts in a way that that guy gets to be the barber. Can't happen. Right? The rules do not allow anybody to win the trophy. Okay? Yes? There can't be two barbers because you only get your hair cut once. Right? Okay, so if they both split the rest of the town, then in particular there's two people, one of which got their hair cut by barber 1, and the other one got their hair cut by barber 2. So Alice got her hair cut by barber 1, and Bob got his hair cut by barber 2. In particular, barber 1 did not cut Bob's hair, violating the rules of barberhood. The barber has to cut everyone's hair who didn't cut their own. You can't have two barbers because then they'd be fighting over, okay, you don't cut your own hair, which of us gets to do it? Whoever doesn't get to do it can't be the barber anymore. Those are the rules. Okay? Now, I want you now to do the following thing. I want you to imagine everyone means every Turing machine. Okay? A person now is a Turing machine. Right? And A cuts B's hair means A accepts B's encoding. This is exactly the same argument. All right? A barber is a Turing machine that accepts every Turing machine that rejects its own encoding. In other words, a barber is a person who cuts the hair of everyone who doesn't cut their own hair. It's exactly the same argument. B cuts B's hair if and only if it doesn't. SR accepts its own encoding if and only if it doesn't. Right? The logic is identical. The words are different and somewhat scarier when we're talking about Turing machines. But the basic logic doesn't have anything to do with Turing machines at all. It's just a simple fact about logic and when it involves things that might possibly refer to themselves. So there's yet another version of this that you might have seen, which is Cantor's argument that the reals are uncountable. Basically what you do is you say, okay, pick any set you want. Okay, pick any function at all from any set to its power set. Right, just any set you like. For every element in that set, I'm going to associate a subset of that set. For example, X might be the people in this room, and the function value tells you the set of people in the room that you like. Okay? So everybody in the room has in their head a set of people in the room, okay, that they like. Okay? Now my claim is not an onto function, meaning there's some set that isn't in anybody's head. Okay? So the idea is I'm going to label an element is sad if X is not an element of its own set. Okay, remember I defined capital X, the set, to be the set of people in this room, and f of x to be of f of little x to be the set of people in this room that little x likes. So a person in this room is sad if they do not like themselves. Okay? And then I'm going to define y to be the set of all x in X such that X is sad. So I claim, for the sake of argument, I like everybody who hates themselves and no one else. I only like people who hate themselves. Right? I'm lying to you, because then if I like myself, then I hate myself, and if I hate myself, then I like myself. And in the real world, that's fine, but this is math. We have to pick. Okay? There is no element little y in X such that f of y equals y. Because if there were, you decide, is it happy? Is it sad? Well, it's happy if and only if it's sad. Okay? So if I want to map Cantor's argument to describe, that there are uncountably infinite sets, I let X be the set of integers, and then I observe, because there's no onto function from the integers to the power set of the integers, the power set of the integers must be bigger. But the integers are already infinite, so there must be a bigger infinity. Right? To map this onto Russell's Barber paradox, I let F be the set of people whose hair you cut. And now you're sad if you don't cut your own hair, and you're a barber if you cut the hair of all the sad people and no one else. So there's no barber. To map this onto the undecidability of self-reject, let X be the set of all Turing machines that halt on all inputs, and let F of a Turing machine be the set of all Turing machines that this Turing machine rejects. A Turing machine is sad if it rejects its own encoding. There is no Turing machine that does everything to the, that accepts the set of all Turing machines that reject their own encodings and nothing else. Right? So it's exactly the same argument in 3 different guises. Now, normally the way Cantor's proof is visualized is you imagine this big table where I'm going to list elements of x down one side, and I'm going to list elements of x on the other. And for each item, I'm going to put a 1 or a 0, depending on whether the element is in the corresponding set or not. And then to construct a counter, to find the set of sad elements, I look along the diagonal and I flip all the bits. Okay. This is why this is sometimes called the diagonal argument, and why self-reject is sometimes called the diagonal language. Okay. Okay. Everybody, this is a lot to wrap your head around, even though it doesn't involve that many words, just because there's this idea of if you have a compiler and you run it on the source code of that compiler, the source code of the compiler is a perfectly well-defined piece of code, and therefore the compiler should do something with it. All right, but what this is saying is there's no way to tell whether a compiler can successfully compile itself. All right, now once you've got this weird self-referential diagonal thing, you can start building on top of it proofs that other languages are undecidable in exactly the same way that you prove that things are NP-hard. So to prove that some language L is undecidable, I'm going to reduce some known undecidable language to L. Okay, and at the moment, the only undecidable language we know is self-reject. Okay, so let me see we can do here. So I'm going to leave the details of this as a bit of an exercise, but or you can just look at the notes. I'm just going to tell you this one. So self-halt is defined as the set of all Turing machines that when you feed their own encoding, they eventually stop. Not necessarily accepting, not necessarily rejecting. Okay. The proof is almost identical. You imagine a machine that decides this, and then you modify it slightly to infinite loop instead of rejecting. And then the machine halts if it doesn't, and it doesn't if it does. Okay, so let me give you a slightly more general-looking problem. I give you an encoding of a Turing machine, and I give you a string. And the question that you want to answer is, if I run this Turing machine on that string, will it halt? Now, this is an example of a language that is acceptable. And here's how you accept it. Using the universal Turing machine, I run M on W. If M halts, accept. That's it, right? So if M halts on W, eventually the universal Turing machine will discover that fact, and it will accept. If M doesn't halt on W, the universal Turing machine will loop forever, but that's okay. I just wanted to accept when the answer was yes. Okay. What you'd really like is a way of examining the code, and I'll even give you the input, and have it tell you definitively, hey, this is actually going to get stuck in an infinite loop in a finite amount of time. Okay? So the question is, if it actually doesn't have an infinite loop, you just run the code, and eventually you'll realize when it halts that it does. But if it does have an infinite loop, that's not good enough because you don't know how long to wait. In fact, there is no how long to wait. It runs forever. What you'd like is another piece of analysis code, a compiler-like thing, to look at the code and say, if you feed this the number 48,317, it's going to infinite loop. Right? So this is the general problem. This is what is known as the halting problem. Given a program, given an input, does the program running on that input halt? Okay? So I want to convince you that the halting problem is undecidable, and I'm going to do it by a reduction from this related problem called self-halt. Okay? So suppose some Turing machine, which I will call H, decides the language halt. Okay? Now, I'm going to build from this a Turing machine that decides the language self-halt, which I know really can't happen. So I'm going to do exactly the same thing that I've always done with NP hardness results. Okay, so H is a Turing machine. It gets two things as input. One is the encoding of a Turing machine, and the other is a string that it wants to run on that Turing machine. And this magic black box, or this magic red box, I guess, which somehow the halting fairy has thrown in my lap, and somehow by magic solves the halting problem. Always says yes or no. Yes if it halts and no if it doesn't. Okay. Now from this I want to build a larger Turing machine that called SH that solves the problem self-halt. And the input here is another Turing machine M, and the output is yes or no. So I've got a Turing machine coming in, and somehow I need to transform that into a Turing machine and its input. We do it. So I've got this compiler. If I feed it a piece of code and an input, it tells me whether this code halts on this input. I want to turn that into a piece of code that does the following. I give you a piece of code. I want to know whether if I run this code on this code, does it halt? Exactly. There's the reduction. Right? So if I want to think of this as something you would do with a Turing machine, I'm going to build this Turing machine SH. All it does is copy the input, make another copy of the input on the input tape. So whatever the input is, it's going to just make two copies of it. And then it's going to feed that doubled input into the magic box for halt. That's it. All right? If the halting Turing machine actually works, this gives me a way of deciding the language self-halt. But I know there's no Turing machine that decides the language self-halt, and so this magic Turing machine here in the middle doesn't exist. Okay? If I could decide halt, then I could decide self-halt, but I know I can't do that. Okay. Now this is a rather simple version of this kind of reduction argument, where the reduction was literally just copy, right? So let's maybe think about something slightly more interesting. All right, so I'll give one more example of this. Okay. So this is something that I could actually imagine wanting. I want like a module that I can attach to the compiler that, okay, I know I can't identify specific infinite loops. I know I can't identify loops that, does this input make the program self-loop? Okay, I can't decide that. But what I'd at least like to do is to be able to identify code that no matter what you give it, it infinite loops. I want to, Turing machine is really completely useless if no matter what input you give it, it doesn't halt. I'd like to be able to identify, to decide, given a Turing machine, whether it's useless or not. Right? Does it halt on everything, or is there even one input where I get an answer yes or no? Right? And unfortunately here, the answer is no. You can't do this. This problem is undecidable. Okay? So once again, I'm going to imagine that I have a magic black box that came down from Asgard that somehow magically solves the problem never halts. In other words, if I feed it a machine, it definitively tells me one way or the other, yes, no matter what you do, this machine is just going to sit on your desk and spin, or no, it isn't. Okay? So the input is going to be some machine, and the output is either going to be yes, it infinite loops no matter what, or no, sometimes it halts. And then I want to build around that machine that solves, actually, yeah, I'm going to solve the actual halting problem. So I'm going to give a machine M, and I'm going to give a string W, and what I want is to spit out yes or no. Now somehow I have to convert that string and that input into the encoding of another Turing machine that it depends on M and it depends on W. I'm going to call it M sub W, not for any particular reason except tradition. Okay. So I have to tell you now, right? So I have to build some magic thing in here that takes M and W as input and spits out this new Turing machine, this new piece of code as output, which I'm then going to feed to my never halt decider. Okay? So the thing that I'm doing inside this box is I'm taking a piece of code, M, and I'm transforming it into another piece of code, MW. Now, this is a little bit mind-bending because the picture that my finger is currently pointing at is a description of taking a piece of code called NH and transforming it into another piece of code called H. Okay? So what I have to imagine in my reduction argument is a program that does a reduction argument. At this point, everyone's brain should be a small, slimy red puddle on the floor, right? The first time you see this, it is incredibly confusing because you'll notice if you're counting carefully, there are at least 4 Turing machines on the screen. There's the Turing machine NH, which I assume for the sake of argument exists. There's the Turing machine H, which I'm trying to construct, which is impossible. There's the Turing machine M, whose encoding I'm feeding in as input to this Turing machine H that I'm building. And there's this other Turing machine that's going to be fed into the magic black box NH. The one cardinal sin when you're talking about these kinds of arguments is to use the phrase, the Turing machine, because there are 4 of them. Right? Sometimes there are 5 of them. Right? So when you're walking through the arguments like this, I really need to be very careful to always refer to things by their names. Right? This magic thing that decides the language never halt, this is NH. The outer box, the Turing machine that I'm building, is H. This is something I claim will decide the halting problem. Right? So H and NH are pieces of executable code. But the inputs to those executable codes are source codes. There's one which I'm going to feed in as the input to the halting problem. That's called M. And there's another one I'm going to feed in to the never halting problem. That's called MW. Okay? So I still have to tell you how to write this piece of source code. So I will do that now. Okay? So I imagine I am H. H imagines that it's somehow given this magic black box M. And it wants to build another piece of code, which it's going to call M sub W. Now, this other program whose source code that H is writing takes as input a string. Okay, let's see, this is a good color. Okay, so it's going to take some string X as its input. X is not necessarily the same as W, but it might be. X is not necessarily the same as the encoding of M, but it might be. X is just a string. Okay. And here is what MW is going to do. It's going to dump X on the floor, and it's just going to take the hard-coded string W, feed it to M, and answer yes or no. Okay? So imagine, if you will, that I have a piece of code that computes Fibonacci numbers. You feed me an integer, and I will spit out the nth Fibonacci number for that integer n. Now, let's call that piece of code Fibonacci. Okay? Now I'm going to put a wrapper around Fibonacci, which I'll call Fibonacci prime. And what Fibonacci prime does is you feed Fibonacci prime an integer, and Fibonacci prime says, screw you, I'm going to compute the 100th Fibonacci number. I don't care what the input is. I'm going to dump it on the floor. I'm going to compute the 100th Fibonacci number every single time. Okay? So M is Fibonacci, MW is Fibonacci prime, W is 100, and X is whatever number you give me. Okay. So one thing that I want you to, one confusing aspect of this that I want to make very clear, this transformation of the source code of M to the source code of MW is being done by an algorithm. This is not a human being doing this. This is an algorithm doing it. And so if I really want to specify how this is done, I need to reveal more about the programming language in which these pieces of code are written. In other words, I need to give you more details about how Turing machines are encoded as strings. But hopefully you can imagine that with any reasonable encoding, I can just add a few extra states to throw X on the floor, hard code in however many states W is in length that writes W onto the tape, and then passes control to M, which, whose description is actually given to you, right? If you were writing this in a regular programming language, you would literally just write this wrapper function that takes int X as input and calls MW. Right? So doing it for Turing machines algorithmically may look a little bit stranger, but if you think about this for a while and imagine what reasonable encodings might look like, it's believable, which is enough for us. We can work through the details if we want to. Okay. Now, MW, this new Turing machine that I built, there are two things it could do. It could halt when it's given its input, or it could not. But MW doesn't care about X. It just throws X on the floor. It just runs W. It runs the original machine M on its hard-coded input W. All right, so this W is being hard-coded here, and this M is being hard-coded here. All right. So if I feed this new piece of code, MW, to the never halt machine, if it says yes, that's only possible if M halts on W. And if it says no, that's only possible if M does not halt on W. Which means this entire machine, H, actually correctly decides the halting problem. But we know that we can't solve the halting problem. And so the only conclusion that we can draw from this is that this magic never halt box doesn't exist. How many people got that? Okay. 2 of you are lying. I've been staring at this stuff for, I first saw this argument, I think 30 years ago. And I've been staring at this stuff actually fairly intently for the last 2 weeks. Because I have to teach it, right? I am walked through the arguments myself. And, after playing with algorithms and having written a couple of compilers and so on, I can play this game where in my own head I can keep track of the various actors. I can keep track of, well, there's MH and there's H and there's M and there's MW. And, it's practice. But in the end, it really is confusing. And there's no way through the confusion except to walk through several examples, which is what you're going to do in lab tomorrow. Okay? One quick question, yes? Turing machines have input. That's it. Okay, final reminder, please come to class for the last 15 minutes on Thursday. If you have friends that don't normally come, please ask them to come. If you have friends who dropped the class, please ask them to come. We want their feedback too. Otherwise, I'll see you. Thanks.